Hello. I'm going to upsolve problem G from second universal cup Ōokayama, stage 20. The problem is called cola. Let me remind what is the statement, what the statement is, and what I was able to find out during the contest. So we have a permutation. Alice has a permutation P, which we will write in zero indexed fashion. And Bob is trying to guess it. What Bob does is Bob names some permutation Q. After that, Alice compares them, finds the first index where they are different. So Pi is not Qi, is not equal to Qi. It finds the minimum I such that it is true, and she tells it to Bob. And if I is n, that is, if P equals Q, means that cola is given to Bob. And this is the objective. Bob wants to get cola. The question is, what is the maximum probability Bob can guarantee to win the cola? So there are two parameters. First of them is n, which is the length of the permutation, and the second one is m, which is the number of queries. So Bob wants to do such queries that m query is simply p, but he of course doesn't know doesn't know p in advance. I don't know. So how to solve this problem? Actually, we can assume that Alice has a random permutation. So if Bob makes, for example, his first move, there is nothing constructively better than just to say permutation 1, 2, 3, etc. n. Because they're not like permutations in a way that you can like combine them, that you can make a composition or inverse permutation. It's just an array of integers with different values. That's it. And they are all indistinguishable. If you can as well replace these 1, 2, etc. n with different letters. The problem doesn't change because of that. So first several moves, Bob's just makes several permutations, and of course he needs to choose different first elements. So if Alice always keeps telling that I equals 1, then there is no need, there is no like sense in taking the same value of Q0 several times, because if you have already deduced that P0 does not equals Q0, you don't have to repeat the same value again, because you again will get the same information and you just wasted your move. So Bob always chooses different numbers. For example, let's just assume that he takes them from biggest to the smallest. Okay, from smallest to... It doesn't matter. Actually, the state of Bob can be defined by two numbers. So at some moment, Bob already knows P0, P1, etc., P k minus 1, but he doesn't know pk plus 1, pk plus 2, etc. what I mean, he not only does he know these numbers, but he also have asked a query which consists of these numbers. So let's formulate like this. He have already made a query in which these numbers are said to be correct, but he has never made a query in which this number is correct, although he knows that it is inside some set of size, let me call it, for example, L. He knows that it is some set of size K. So you already know these numbers, but you have K options about what PL can be. So this is our state. Actually, since you have already guessed these numbers, you can forget about them. You just now have a permutation of length n minus L, and that's it. So we can forget about it. So let's write some function, f, and it has 3 arguments. The first one is n, length of the permutation. The second one is m, is k, which is the number of options of P0. And the third one is m. M is the number of questions that you have. And this is maximum possible probability to guess. Okay? So again, let's go, actually. So let's start with the initial conditions. So assume that, first of all, k is at most m, of course. Yeah, if you have a permutation of length n, then you can have at most n options about the first element and any other element. So let's start with 0, 0, m. This is always 1. Since you have n equals 0, this means that the part which you have already guessed is the whole permutation, and the part that you haven't guessed yet is empty. So this means that you have already guessed the whole permutation, and this means that you know that it is, you have already guessed the permutation, and the answer is 1. The second thing, and it doesn't matter what m is, it can be 0, it can be greater than 0. The second question is, what if we have n is greater than 0? Yeah, for example, n is at least 1. K is of course also at least 1. But m is 0. In this case, it is sad because there's still an element which you haven't guessed yet, and the answer is 0. Even though you might know the permutation, for example, in case of f110, you know the permutation is just 1, but you cannot receive a caller because Bob identified P, but he didn't make a query with this P. So this is 0. Finally, it is interesting to ask about k equals 0. And k equals 0 doesn't make sense if n is at least 1, because you have some permutation. But the problem is, it is impossible for a permutation to not have any options of the first element. It's just impossible. So let's say that it is undefined. Okay, we have formulated the initial conditions. Now let's think about reductions. So let's assume that n, k, m are such that m is at least 1, n is at least 1, and k is between 1 and n. Okay? So what can you do? All we can do is we can take just any permutation of size 1, or not of size 1, but with the first element which we didn't try before. So if we guessed it, it happened with probability 1 over k. Then the only thing left is to guess the remaining permutation. So we would like to write like this, n minus 1. Since we don't know anything about the second element, it's again n minus 1, and m minus 1 because we have spent one question. However, it is not correct. Yeah, because, for example, assume that we guessed that the first element is 1, but also possibly you have guessed the second element, which is 2. Maybe we didn't, but maybe we did. So if we have guessed the first element, then actually we got an extra question to guess the remaining n minus 1 permutation. So actually it is m here. We still have one question. We still have this question. Okay, however, with probability k minus 1 over k, we didn't guess it. So we have to guess again. That is n k minus 1 and m minus 1. Excellent. Let's go on. The problem is actually that if k is equal to 1, then this is 0, and as we said, it is undefined. However, it is not a problem, because this k minus 1 is multiplied by this k minus 1. So actually, even if it is undefined, it will multiply, if it will be multiplied by 0, so it is 0. So it doesn't matter. Let's continue. Since, as you saw, it really makes sense to consider a new function g of n km, which is equal to k times f n km, not only because it removes the problem of this value being undefined, yeah, because it is always multiplied by 0, but also because, for example, this value, it isn't multiplied by k, but the remaining part is divided by k. So if we multiply it by k, we get k times this, and this is removed. So we would like really to consider this new function g. And f of nkm is simply g of nkm over k. Let's rewrite this equality. Namely, let's find g of nkm. So as we see here, we need to multiply k times f nkm. This is equal to this part multiplied by k. This is simply f n minus 1 m minus 1 m, no, n minus 1, plus k minus 1 over times f n k minus 1 m minus 1. And now we can substitute this thing, and we know that it is g of n minus 1 m over n minus 1 plus g of n k minus 1 m minus 1. Note that nothing bad happened about case k equals 1, because here it's actually 0. Yeah. So now it is some number here. This number is simply 0 times undefined. So we can assume that it is 0. Now let's rewrite our initial conditions. They somehow changed. Not much, but they changed. So again, we know that g 0, 0, m is again 1. We again know that 1 or not. The problem is we divided by k. Yeah? We have divided it by k. So does it still make sense? Okay, let's think about this part. What if here n equals 1? So it is now 0, 0, m. Does it still make sense? Not really, because we cannot divide by n minus 1 in this case. So we need to make some changes about case n equals 1. So let's think, what do we have if n equals 1? If n equals 1, then we have the following. So g 1, 1, m is simply, is it true that m is at least 1? Yeah, and we cannot rewrite it like this because we will end up with division by 0, and we don't want it. There is a way. Let's continue rewriting it. No, I don't want to continue rewriting it before I have something that makes sense. Let's for now write like this. Let's continue. So what if n k0? G of n k0 is always 0. And this is true. F of n 0m is always also 0, just because we have multiplied it by k. G here. Let's continue then. Now you can see that, you can clearly see that it makes a lot of sense to multiply this by n minus 1 factorial. Why is that? Because if you multiply this number by n minus 1 factorial and this number by n minus 2 factorial, yeah, as you see, it is n minus 2 factorial here. Or divide. Yeah, let's divide it. So we would like to have n minus 1 factorial in denominator here. Because here it would appear n minus 2 factorial, and here would appear n minus 1 factorial. And you can remove all of them. This makes a lot of sense. Let's try to do it. And in order to do that, I need to create a new function. Let me think. I don't like something. It seems I need to divide by n minus 1 factorial. Okay, I think let's write like this. So h is g times n minus 1 factorial, and g is, of course, h divided by n minus 1 factorial. Let's rewrite what we have now in this condition. So h nkm is equal to, we need to multiply n minus 1 factorial times g nkm. Now let's substitute this formula. So we know that it is equal to n minus 2 factorial times g of n minus 1 m plus g nk minus 1 m minus 1 times n minus 1 factorial. And now let's note that it is easily rewritable as h, because g is simply h divided by n minus 1 factorial. So if you rewrite it like this, you see that it is simply h of n minus 1 m plus h of n k minus 1 m minus 1. So this is our formula. And we need to work out how we continue, how we calculate it. To calculate it, I think, what do we need? To calculate it, I think... So let's again write the initial conditions. Let's start with it. So now we have the following. So we need to multiply all initial conditions by n minus 1 factorial. It's still like this. So h11m is m at least 0, and g nk0 equals g, or h n0m equals 0. Okay. And we need to find some value of this number. So first of all, first things first, I really don't like k a lot, so I would like to remove k. To remove k, let's introduce new function. Let's actually introduce two new functions. So we have two new functions. One of them is h nkm, which is simply sum So let's like explain this in on idea level. We have some situation. We try something and we failed. So now we have one question less and one option for the first element less. What do we do then? We again have to do the same thing. We need to again try some new permutation, and again either we win or we lose. And if we lose, we need to do it again. So let's rewrite it in terms of doing it again and again. That is, let's try the following. So let's say that I try let me think. From 0 to minimum of m and k minus 1. H of n, k minus I, m minus I. Let's sum this thing. This is what I think we need to do. Let's find this sum. Okay, let's rewrite it. So sum of I equals 0 to this minimum of m and k minus 1. So what do we have here? So first of all, it is h of... let's apply this formula. So if we just have something... and we are assuming that n is greater than 1. Because if n equals 1, then we don't need anything to do to work this out. So h of n minus 1, n minus 1, m minus I plus h of n k minus I minus 1 and m minus I minus 1. Great. So let's calculate some new function q. Q of n, k, and m is simply the sum of h of n, k, and I for I from 1 to m. So let's rewrite it as two things. So first thing is h n minus 1, n minus 1, m minus I plus sum h n k minus I minus 1, m minus I minus 1. These are two things. Okay, let's start with this one. So note that it is again going through all i's. Let's rewrite it as this, like this. So it is from I equals 0 to minimum of m minus 1 and k minus 1. And we have here h of n, k minus 1 minus I, m minus 1 minus I. Here we have the same thing. Okay, the interesting part is that note that if we take exactly this minimum, then it is a 0. Yeah? Because either this is 0, and as we said, it should be 0. Or this thing is 0, and it also doesn't make a lot of sense. So actually, you can just replace it with minus 1 because you just removed 1 0 because of that. So now we simply have h of n, k minus 1, m minus 1. This is interesting. Okay, what about the left side? In the left side, so if we sum it up to infinity, it is simply q of n minus 1, n minus 1, and m. But we remove all addends starting with minimum of m and k to infinity. So we need to subtract q of n minus 1, n minus 1, and so see, here starting with m minus this minimum, we don't take this addend. So we need to write here m minus minimum of m and I. Great. So let's rewrite what we have. We have that h nkm equals q n minus 1 n minus 1 m minus q n minus 1 n minus 1 and actually maximum of 0 and m minus I, and plus h n k minus 1 m minus 1. Not I, but k here. Now let us subtract this and this. So we move this, add it to the left side. Note that if we remove, if we subtract h and km and the previous h k minus 1 m minus 1, then we simply are left with this one addend, which is h n km. So we actually have the formula for nkm, which is q of n minus 1 n minus 1 m minus q of n minus 1 n minus 1 and some maximum. Okay? So if we can calculate this number q for equal numbers n and k, then we can calculate any little h. So now we are left with the following task. So let's define q and m as q n and m, and we need to calculate q and m. We again need some initial conditions and recursion step. Let's write them down. So initial conditions. What are the initial conditions? So I guess it is simply q1m and qn0. So this is what we need. Let's look at the definition of q. Q is simply sum of all h's from 1 to m. Okay? So it's easy to see that it is 0, because you sum 0 h's. Okay, let's rewrite this one. This is simply sum of I equals 1 to m, h 1 I, and it is simply m. So now we have an initial condition of this being equal to m. And finally, we have some step, which is q and m is equal to sum of I equals 1 to m h n and m. Now we know that it is difference. Okay, note that in this formula, this maximum, it is simply equal to 0. Yeah, because we only have we always have n is at least m, actually. Or do we? Do we always have n as at least m? Maybe not. Okay, it may be both ways. M can be less than n, or m can be greater than n. So we need to write both options. Let's write them down. So here we have q n minus 1 n minus 1 and I minus q of n minus 1 and minus 1 and this maximum. So maximum of 0 and I minus n. Yeah. I don't like something. I don't like it because I have a reason to not like it. Now I have some strange sum. Maybe we need to go back here. Maybe we need to go back to this formula. Maybe we really need to go back to this formula. Well, I don't know. Okay, no, I don't like it. Let's not do it. Or do we need? No, we actually need to do it. We need to find the function q. This is what we need. We need to find the function q. Okay, if we need to do it, then let's do it. Unfortunately, let's do it. Okay, so we clearly see that the problem for n is reduced to problem for n minus 1. So let's rewrite it like this. Let's write like this: Qn of m equals sum for all i's, Qn minus 1 of I minus sum for all i's, Qn minus 1 of maximum 0 and I minus n. Let's think about it. So let's take j equals I minus n. So if I equals 1, then j equals 1 minus n to m minus n. So here we have Qn minus 1 of maximum of 0 and j. And now note now let's replace it with simply j, I think, and we can say that q of something which is n and less than 0 is also 0. We can make this definition. So here we have simply j. Okay, now note that this number is definitely negative. So we can replace it with 1. So sum from 1 to m minus 1, it is still qn minus 1 of j. So we have sum so we have this difference of sums. Yeah, beautiful. So assume that we have some array qn. Then what is the value of array qm? Let's think. So we have some array qm. How is it qn given array qn minus 1? How do we calculate this value? This seems like we simply need to sum all numbers from m minus n plus 1 to m. Does it look like this? I think it does. Yeah, because if m is greater than n, then we really removed some constructive elements. But if m is less than n, then we simply added some zeros, but this is not any problem. So qn is sum of this element, this element, this element, etc., and this element, and the number of these crosses is n. Okay? Okay, so actually it looks very similar to some convolution. So what is qn of m? Of m? Yeah, of m. We need to take qn minus 1 convolution with n ones. This is not quite correct right now because it is correct right now. It's simply this convolution. Yeah? Yeah, it's simply this convolution. It seems that it's simply that convolution. Great. So actually, now to calculate qn, we need convolve several arrays. 1 times 1, 1 times etc. times n ones. Instead of convolution, we need to take it as a modular operations. So let's say that this is simply 1 times x plus 1 times x squared plus x. So we replaced the sequences with their generating functions. So this is our task. We need to calculate it. And finally, we can replace it with the following. We need to find 1 times 1 minus x times 1 minus x squared times 1 minus x cubed times 1 minus x to the power of n, and all of this is divided by 1 minus x to the nth power. This is our problem. Let's rewrite it like this. Let's rewrite it like this. Product of I equals 1 to n 1 minus x to the power I times 1 minus x to the power minus n. Okay, so this can be done via Newton's binomial formula. So as we know, 1 plus x to the power alpha is sum of x to the power I times choose alpha I, where choose alpha I is alpha times alpha minus 1 times etc. times alpha minus I plus 1 divided by I factorial. This is famous formula. So we can rewrite it for our case, and we get sum of x, it's like infinite sum, of course, x to the power I times choose minus n I and times minus 1 to the power I. Okay, let's rewrite it with factorials because it makes more sense. So x to the power I times, okay, this will go from minus n to minus n minus I plus 1 divided by I factorial and times minus 1 to the power I. Note that actually this minus 1 to the power I beautifully fills these holes here. So these all becomes, these all numbers become positive. So actually it's now n times n plus 1 times etc. times n plus I minus 1 divided by I factorial. And this is beautifully simply choose n plus I minus 1 I. Great. So we have calculated this, the right thing. So we need two things. We need to calculate the left thing and we need to multiply them. So multiplication can be done with f15. The problem is we don't know what this is. And during the contest I wasn't able to calculate it, unfortunately. Because it needs some special knowledge, which is called Euler's Pentagonal theorem. Okay, let's look at it. So, Euler's Pentagonal theorem states that this infinite product, yeah, we actually don't need infinite, we need only first n multiplicants. But note that if you take the bigger and bigger multiplicants, they don't affect the first n coefficients. So we can as well take the infinite product. It is said that it is this infinite product infinite sum with really rare coefficients, which are plus minus ones. Yeah, as it says, a striking feature of this formula is the amount of cancellation. Yeah, because if you, for example, take the first n multiplicants, if you do it naively, you get 2 to the power of n multiplicants. So quite a lot. However, out of these 2 to the power of n multiplicants, they cancel out to square root of n summands, because this thing grows with square growth. It has a square growth, power of 2 growth, and this means that below n you will get at most square root of n times constant non-zero values. There are some beautiful proofs, which I don't remember. Okay, but actually, you can just not prove it and just write this formula. So the only problem left is to multiply them, and we can do it via simple FFT. Okay, I will be back in several seconds. So let's write down what we need to do actually. So first of all, we have some Qn, which is a polynomial, which is calculated as let's somehow denote it. So Euler's function, this is called Euler's function phi. Okay, let's write it like phi. So we need to take phi and multiply it by 1 minus x to the power minus n. Which is written like this. Which is just simply this sum. Okay, now we know all q's. After that, we need to find h, n, and m. Let's remember how it is calculated. It's calculated simply as the difference between n minus q n minus 1 n minus 1 m minus q of n minus 1 n minus 1 and maximum of 0 and m minus n. Yeah? Yes. So note that in the statement it is said that m is at most n. So actually this means that this is 0. And since this is 0, then we simply have this thing. Great. So it means that we need to take n minus first polynomial and take its mth coefficient. And this means that we needed modulo x to the power m plus 1. Yeah, we needed modulo x to the power m plus 1 because we want its mth coefficient. Let's go. Now we need to calculate f n m, which is g of n m divided by n, which is h n m divided by n factorial. Yeah, because we these two are different by the factor of n minus 1 factorial, and since we also have n here, it is divided by n factorial. So that's it. We need to find some coefficient and divide it by n factorial. Let's do it. So first of all, let's make the multitest. To do that, we need ifdef on home, I think. Is it home? No, it's on PC. We open input txt and stdout. Then solve tests. And in solve tests, we go through all tests. No multitest? Well, we will still use multitest. So if not solve test, return false. Not return false, but just return. Now let's write the function solve test. How do we write this function? So if we fail to reach n and m, we return false. Otherwise, we print find ans of n and m and return true. And we define n and m as just two ints. This is done modulo this modulus, which is compliant with FFT. And finally, we need to find ans. Actually no. We don't need the FFT. See, we only need one coefficient of this thing. And since we only need one coefficient of this thing, we can do it in linear time by looking at coefficients of left and of the right multiplicand. So, what do? We take A equals find Euler of nth of n of size of size m plus 1, and vector int A equals find inverse x minus 1 minus x of power n and also m plus 1. And then we need to find the mth coefficient of their product, which is simply int ans equals 0, ans equals sum of ans and product of ai and b m minus n. In the end, we need to divide it by n factorial. So we say that return product of ans and factorial of n, and since it is inverse factorial, I write true here. Let's start with factorials. It's rather simple. I say that I need static vector int fact and inverse fact. I also need const int n, which is the maximum let's write like 2e7 plus 10. And if factorial dot size is less than n, then I need to calculate factorials and inverse factorials. Let's do it. Fact dot resize n1, inverse factorials dot resize also n1. Then if from 2 to n factorial I is product of factorial I minus 1 and I, then inverse factorial dot back is inverse of factorial dot back, then from I equals n minus 1 I at least 3, inverse factorial of I minus 1 is a product of inverse factorial of I and I. Now we need several functions. Let's start with the easiest ones, which is sum. Int a, int b, int m equals m. If a plus equals b is at least m, a minus equals m, return a. So sum. Now let's find the product. And here it's also easier, return long a times b percent m. Now we need three functions. Inverse, find. Actually, I also need one more function, which is choose. Int choose n k. And it is return product of factorial n and product of factorial k but inverse and factorial n minus k and also inverse. So the choose is written. Now we need Euler and find inverse 1 minus x. Let's write inverse. So return a equals 1, 1. Then what do? I always keep forgetting about how it's written. Let's try. So I need to take inverse ampersand a and a. This is definitely what should be done. And this is something which is inverse m modulo a. So I would like really to multiply it by a. By m. So now this is something which is 0 modulo m and 1 modulo a. Now I do like this, and now it is 0 modulo a and 1 modulo m. Since it is 0 modulo a, I can divide it by a. Now it is inverse a modulo m, but it is negative, so I need to add m. Okay, now find Euler and find inverse 1 minus x. So let's write the easiest one of them. And let's look at the formula. So the ith coefficient is simply this choose. So let's go. Ans I is choose of n plus I minus 1 I. That's it. Finally, we need to write a function find Euler. also like this, and it is relatively simple because the function is written in Wikipedia. So we start with, so if m, then we say that ans0 is 1. Then let's go through all possible i's, starting with 1. So we need to calculate both indices. Int index 1 is I times 3 times I plus 1 over 2, and I2 is I times 3 times I minus 1 over 2. Let's see if we wrote them correctly. Yes, we wrote them correctly. Now if I2 is at least m, we break. So if I1 is less than m, we say that int coefficient equals, so if I is odd, then minus 1. If it is even, it is 1. So if I1 is less than n, then ans I is simply coefficient. If I2 is less than m, then I1, sorry, then ans I2 is coefficient. Else we break. That's it. I believe we have finished. No FFT. And since no FFT, we are happy. Factorial must return a value. Because we need to return inverse I fact n or fact n. And we need to write inputs. 2, 1, 1, 1. And 167, 91. Let's see if it works. 499. Okay, this is correct, but this is something strange. This is something strange. Maybe we need some smaller numbers. So let's look at, so 2, 1 and 1, 1 are correct. Let's look at 2, 2 maybe. It says 0, and this doesn't make sense. It cannot be 0. It cannot be 0. No. But it is 0 here. So let's look at A and B. These are some square polynomials. So it's like it's like 1 minus x squared times 1 plus 2x plus 3x squared. And we need this coefficient. So this is minus 1, minus 2, and plus 3. And it is 0. However, it doesn't make sense. It doesn't make sense Ah, we need n minus first. Do we need n minus first? Yeah, we needed n minus first actually. N minus 1, why? Because here we have a negative choose. And why do we have negative choose here? Because n is 0. What? Okay, actually it's easy. So if k is less than 0 or k is greater than n, return 0. Oh, this is nothing but hard. Okay, now it's worse. Worse. Now it's much worse. Okay, what I don't like it because it didn't work. So I want the following. I want 1 times 1 plus x maybe we need some initial, maybe we skipped initial conditions. Yeah, for example, our formula maybe doesn't work for this one. So, because I see. I also need to multiply it by all ones, and I didn't do it. I need to multiply it by all ones, which is simply 1 over my 1 minus x. So actually, yeah, actually it's true that you need initially. So the formula is not like I wrote here because it should be n plus 1. We need to divide by 1 minus x one more time. So we need to make a convolution of several things. 1, 1, 1, 1, 1 times 1 plus times 1. And times 1, 1. Do? Yeah? Okay, and we say that it is Maybe I understand what happened, what went wrong. So maybe it's not quite Euler function because of what? So we have E equals product of 1 minus x to the power of I. But we have only finite product. We have E what? We need to find En, which is product from 1 to n. The problem is that these two are not equal. It's fine to take them modular x to the n plus first power, because starting with n plus first power, they are not different. However, we are taking them modular x to the power m plus 1. So the one coefficient is incorrect. Actually, we need to find it modular x to the power n plus 2. And this is the problem. What? Then why is this incorrect? Maybe I don't understand something. Okay, let's now fix this problem and then think about the other problems. So here, actually, if we need to find En modular x to the power n plus 2, and sometimes we do, then we do it incorrectly, because En is not equal to E. Actually, it's still not very hard, because it seems like we need to calculate En plus 1 divided by 1 minus x to the power n plus 1. Then we can take instead simply Euler function phi divided by 1 minus x to the power n plus 1. And actually, modulo this number, this is simply phi times 1 plus x to the power n plus 1. Moreover, it's simply like phi plus add 1 to the coefficient. So exponent plus 1. Yeah, so it seems like we need to write here if, let's also give it number n. So if n equals m plus m minus 2, then we also say that ans m minus 1 equals sum of ans m minus 1 and 1. And here we need n and m plus 1. Okay, now it is, so 1 1 is fine, 2 1 is fine, but 2 2 is not fine. 2 2 is incorrect because if we have two questions, we can get the caller definitely. So why does it say that we cannot? So maybe we need to continue working on with pencil and paper. So I want to say that h 2 2 2 is simply 2. Yeah. First of all, let's make sense. Let's be sure that our formulae comply with it. So h is sum of n-1 and n-1 and n. Yeah. So let's write it down. So it's h1 1 2 plus h2 1 1. Okay, now this is simply an initial condition of 1. And this, let's rewrite this one. h211 is h111, which is again 1, plus h200, which is 0. So this is definitely 2. Okay. Now let's find out what do we have here. We know that our formulas say that h, n, and m is q h 222 is q 222 plus minus no not 2 q 112. So it says that it is q 112. This also makes sense. It is also 2. So we need to calculate q 112. And it is the following. It is a lot of ones. Maybe it's not. Maybe it's not. Maybe I messed up it again. So here actually the initial condition of q is m. So here we have all of this should be multiplied by q1, which is 1, 2, 3, 4, etc. So this is actually squared this thing. So we need actually n plus 2 here, n plus 1 here. Don't we? Now it's strange. Now it's strange, really strange. Yes, so it is like this. Okay, starting with 0 actually. 0, 1, 2, etc. And we take the second coefficient. So yes, this is definitely just 2. No question asked. No questions asked. Hmm. Mm-hmm. But we multiply it even one more time by 1 minus x inversed, 1 minus x inversed. So it should be 1, 0, 1, 3 here. Why it starts with 1? What? I get it. The problem is this array is not... It is times x, I mean. It is times x. So it's x over 1 minus x squared. And since it is, we have to respect that. So let's respect that. And do it starting with 1. So like this, like this. Now it works in linear time. Cool. Let's submit it. Well played.